Okay, so let's begin. I'm going to talk about a few examples with the delta method. Examples are probably better than a proof in the first place, but we've at least shown ourselves this method is supposed to work. And so we'll talk about that a little bit more as we go through the examples. And then I think we'll kick things off with a brief introduction to Bayesian statistics. I'm going to try to pull all this stuff together that we've been talking about. We've been bouncing around a little bit, and out of these different techniques, we're going to build a big comparison. I'm going to ask you to do that on your homework. And so I'm going to walk you through everything. It's actually going to pertain to this example right here. And so you're going to study this example using delta method, bootstrapping, and Bayes. And so I need to tell you more about Bayes, but you can probably get started on this. And I'll tell you what it is I'm going to ask you to do. Let's just kick it off with this example right here. So I've got some expectation that I've worked out. I know expectation of my random variable. And this is going to be a function of n, and it's going to have all the properties that we need for the delta method to work. Okay, so what do we need for the delta method to work? So I'm not just going to say this, but I'm also going to say all the conditions that we need on x to apply the delta method. What are they? X such that the delta method works. And I'll say is applicable at least. What is it? And this is where I'm going to snag you on your exams, because I'm going to ask you these things. When can you apply it? So I'm not always just going to ask you to work out a calculation. We'll see if you've checked the conditions. So there's conditions. And if you've been reading the book, you know the answer to all of these. They're all in the book. So again, book is a big part of this class. I mean, the lecture is cool. So, but there's details in the book. Elise?
They have to be independently.
Okay, IID stuff, kind of. So, something much stronger that we need, but maybe we can apply the delta method when things are IID or not IID.
I have another guess.
Okay.
Variance design.
Okay, cool. You know, so we're homing in on things. So there is a variance, and we do need that. Put it all together. One more thing. Yeah, this sort of central limit there. That's all we really need. So we need x root n minus theta converges to a normal 0 sigma. So this says a little bit about what Elise was saying. There's a variance in there, got to have it in there, so it better exist. If it didn't exist and we had to throw an infinity right there, that would kind of spoil the game. Just keep in mind, this is a function of n right here. So as I take this limit, n goes to infinity, then that holds. Now, I usually put on an n right there, but usually our test statistics are functions of all of the data. So a lot of times I just remind you when we're taking a limit, I really like to build it into the notation. When I use that, it's kind of a knob that I'm turning. Let's see it. So we need this condition to be true. And then we can apply delta method. And delta method is going to give us a normal approximation to this transformed random variable. Okay? So the original random variable is asymptotically normal. I'm not sure we needed exactly IID to be able to say this. So that's where it's like, yeah, it's true. In these IID cases, a lot of times we're dealing with X bar right here and then. Yeah, that's good. But that might be a little bit too strong. All we need is this statement to be true. That is true for IID stuff with finite variables. So pretty close. Okay. So the original random variable is normally distributed, mean theta, variance sigma squared over n about. That's how we use it. And we want to know about this transformed random variable. And delta method says that this will also be kind of like a normal. So this is an asymptotic statement. So again, as a function of n, we have a statement concerning g of x to the n minus g theta. Root n goes to a normal. Remember, delta says this. Gxn minus g theta root n goes to a normal. Mean 0 because I've subtracted it out right there. I'll approximate the mean probably when I use this thing. But we can at least make a theoretical statement about this. G prime theta squared variance of xn. Whatever that original variance is. So it's another normal, it's centered somewhere else, and it has a scale multiplier on here. Delta method. So pretty cool, right? When I saw this, I was like, this is fantastic. I understand it. I could even do the proof right now. I don't even need to study the proof, because I know what Taylor's theorem does. So it's just this argument of root n times the remainder term goes to 0. If you've been reading your book, they apply Slutsky's theorem to prove that to you. And so if you want to be a PhD student, you'll know what that means. So in statistics, I should say. So it's these limit theorems. I have two random variables multiplying by each other or adding each other. How do they converge? They converge in the intuitive sense. They converge, what it says. This isn't a measure theory class. We want to focus more on how we use some of this stuff, but all that's important still. So this is just going to converge to some other normal. We need to figure out which one it is. So what are we going to do right here? What do I plug in right here? Applying the delta method. Direct transform. Kind of looks like Jensen's has something to say about how good that is and which side it's bounded by, but the delta method says it's converging to this. So this kind of statement is a function of n. If n is bigger, this seems more and more true. Okay. Jensen's inequality is getting tighter and tighter. If that were a convex function. Delta method didn't put any statement on g, right? Any old g, right? Yeah. There is a statement about g. And I really like the delta method because if I just kind of stare at what the claim is, I know what the assumption is. This has to exist. Must exist. So that's a smoothness statement, but also we know this cannot be 0. Otherwise it has no variance, and that doesn't make any sense to us. Example 3 will allude to that. This is what's going to happen there. So you don't need to work it out yet, but 2 times mu if mu is 0 is going to be 0. You're going to have real bad problems. Okay. So there are a few statements here about what G is, but it didn't say it needed to be convex, like in Jensen's inequality. So it's good to get these things untangled in your mind. And so in this thing right here, I just need G prime theta squared variance of x. I'll put the n on there if you want. Let us all know it's a function of it. If you'll see statements made where they don't explicitly put that on. And so, and I can work that out, because I've told you the transformation. So this is just 1 over theta squared minus sine squared. Make sure that squaring is there, because if you report back a negative answer, if I did see this on an exam, I imagine it would irritate me if you did have a negative number right there. And it's because it doesn't make any sense. Variances have got to be positive. They're positive quantities. They're expectations of squared stuff. And so, but this will always be positive. So something to note, that square's doing something for us. So that's what we'd do. If I knew what the random variable was that I was playing around with, I could compute that. Now, I want to just point out, this right here is a function of theta. It'll have something to do with the original parameter. Okay, so this is just kind of a theoretical statement. You know, limiting wise, this starts to look more and more true. So if I actually knew the true parameters, so if I were doing a simulation study, I could repeatedly sample my xn and then repeatedly transform it. And I could draw a histogram of that repeatedly transformed stuff. So these go back out into the universe, resample over and over again. What distribution does this look like? This is the one. That's what the delta method is telling you. Please.
Where did the root n go?
This root n right here, it shows up in here,
From the delta exponential.
in this. So I would have the n
Okay.
show up here. I'll be more explicit in this example and you'll see it up here. But it would be appearing here. So, makes sense. So if that was x bar right there, that would be sigma squared over n. When I factorize out that n, that's out. So, delta method is saying to us, at least practically how we use it, this random variable has this normal overlay. If n is big, and that linear approximation is good, it eventually gets good. So that's what n big is doing for us. Then these will look very similar to each other. So I'm going to ask you to do this exact same thing on this problem, on the simulation homework. So pretty easy setup. It's all IID stuff. We'll sample n things. I goes from 1 to n. And I'll have you simulate lots of what we would plug in for our expectations. I want you to only use the data. You can also use the parameters if you want and see how it changes. But if I didn't actually know the parameters in all of this, I put hats on them all. I would estimate that parameter. So let's do that example right here so we can see what I mean. So there's a statement that the delta method makes, which is all fine and dandy, but we don't know theta in the first place. I want to back up just 1 second before we go into this example, and you'll see all the little layers and details. Mohammed?
I'm sorry, why did we just call this a linear approximation? What's linear about that?
Delta method. It all relies on the first order Taylor approximation.
Oh,
That's a linear function. So that's the linear assumption. Yeah, that doesn't look too linear if you start writing things down. But how did we derive all this? It's through a linear approximation to true G. Got a lot more to say about that through these examples. But before I do example 2, Elise came up at the end of class and said, I don't get it. Why don't you just transform the random variable? Why this approximation? Just transform it. So can anybody help us with that? Mohammed?
well, you'd have to do all the clunky calculations associated with that. This is like lazier and much more convenient.
Lazier, way more convenient. Nowadays, it's a really good question though. And so I don't know if we have to be so lazy because we have these things that they don't really get exhausted. So, but we do. And this knows how to do a lot of calculations. Remember back in the 1960s, we can at least imagine, I wasn't born then either. This might be the only gig in town. So you've got a normal table. You don't even have a computer near you. And so I can say a lot of things about normal distributions. And so what the delta method is telling us is that this thing is becoming more and more normal. But early, when n is small, it's probably not quite there. And so we could do better calculations, better approximations for smaller n if we actually did the real transformation. And so on a computer, I'll try to convince you throughout this class, you can always draw any random number you want. So I could sample true G with my computer. In the 1950s, I'm out of business. So it's only because we have those that we can do these calculations. Saying that, I do like the delta method sometimes for proving stuff, what happens, and sometimes I see people use it there and they'll come up with a proof and I go, cool, right on. I understand too. But sometimes I see people apply this in practice and I usually chuckle just a little bit because you could do something better. So maybe this is a theoretical tool for us. Maybe you actually use it, but I would encourage you to check how well it's working because there's a lot of statements about approximations. And if n went to infinity, if I actually had infinite amount of data, I don't need to be a statistician. So this thing just collapsed to a point. I know what it is. So I think we actually do need to check, see how well this thing works. Not my favorite tool, but still kind of a neat tool. I'll teach you a little bit about probability too. Let's look at this example. And this is what I'm going to have you practice on the homework. So you'll do a simulation study. And so our G function is this, just to be explicit. So I know how to estimate P in a way such that the delta method's assumptions hold. How would you estimate P? Be real clear about this. This is a 0 or a 1 or a 0. This happens with probability P. And this happens with probability 1 minus T. This is a coin flipping model where I've encoded the heads into ones, the tails into zeros. Typical setup. How do you estimate P?
Take the average of the size.
Yeah, you guys are all on it now. Take mean, all that stuff. So there are probably other answers too. Anybody have a different answer other than the mean? Cool. That's fine with me. So we'll have one by the end of that lecture as well. There's other ways to do things. But the answers are mostly going to be kind of like the mean. And they'll all converge to the mean. So any sensible person likes the arithmetic average for this. But sometimes you might want to penalize it. And I'll show you why a little bit later. So X bar. I'll put the n right here. If you prefer, but it's just this. We just ask a couple questions about this, make sure we have reasons, because that's what we're doing, coming up with reasons for doing things. Why do we like that answer?
Because an expectation is equals.
Okay, so one of the weakest answers, but it's unbiased. And I like that. I usually like it if I get it for free. But I'm usually not willing to work for it. So I care about being close on average, not just being about that. Variance has something to do with properties of estimators too. Saying that, this is minimal variance too. We'll learn that in chapter 7. So this is minimax. It's got all kinds of properties. Good stuff happens with this estimator. It's also normally distributed asymptotically. So I can make probabilistic statements about it. Saying that, I probably wouldn't exactly do that. I'd probably do more exact things than jumping straight to the asymptotics. But if you've taken a Stat 101 class, you probably assume that thing's about normal. You've probably come in and said, well, what happens when the normal tail goes out through the negative side? What does that mean? You say, well, maybe truncate it. Or, so it's kind of a peculiar answer to say this is normally distributed, where that goes between negative infinity and infinity, where this thing lives between 0 and 1. So I don't like the asymptotic answer because it's just tacky, but it's probably useful when it's big. Saying that, if you do compute confidence intervals and you have a negative thing hanging out the side, you need to do something different. So I know how to estimate P. This is my P hat. So, and I know my expectation of this thing p hat, which is just x, and I'll put the bar over so we know what it is. This is p. Central limit theorem applies to this. Kind of. The asymptotic statement is still true. And sometimes useful. Okay. So now we need to come up with an estimate way of, we're going to apply the delta method to this and use that normal approximation. So GP is kind of, this isn't exactly the asymptotic statement. I'm plugging things into the other side and I've got my n over there. I can't just limit through, but it looks about like that. So it starts to look more and more normal over that histogram as n is bigger. So what do I plug in right here? Yeah, exactly. Just plug that thing in. G. That's it. So this one's slightly more work. G prime P squared variance exponent. So let's work on that.
Is GP hats not GP, right?
Good question. What are we going to do with it? So what does the delta method say? Were there any hats in there? No. So I'm making more of the delta method statement. Now when I go to want to use this thing, I'm going to start throwing hats all over it. There's a difference. So the delta method makes a statement using P, and you know it walking in. What do we do with it all? We plug in P hat eventually. So these are all functions of P. This is a function of P. And I want to remind you this is also a function of P. So function of P.
I'm sorry, I mean the first one.
Oh, got it. Just pause. You're right. This is a test. Okay. Hopefully that made some sense, even though I was trying to confuse you. So hopefully you didn't get confused. Mohammed?
So this is an approximation of an approximation. And we said that the delta.
It's an approximation.
Yeah, but we said earlier that the delta method converges at the speed of square root.
Linear approximation, and then there's the asymptotic statement. I don't think of approximations of approximations. There's only approximations.
Okay, but does this
But
have a
it-
different rate of convergence?
Asymptotically, it's the same. But there's constants. Does that make sense? So eventually, as I look at the graphs, they come up to each other. But at any finite n, they're separated. So asymptotically, we would say they have the same rate of convergence. So if we were in math class, I would say no. But any engineer will tell you they're different. And so practically speaking, yes, but asymptotically, they have the same root n rate of convergence. Constants do matter. Eventually, the rate's time. That's kind of how you think about it. That's the asymptotic statement. Okay. So this thing right here, all we need to do is take the derivative of p times 1 minus p inverse. So I'll just write it down that way. And so this is going to be 1 minus p inverse plus minus 1 minus p minus 2 chain rule plus. Two negatives show up there. Okay, so we want to just simplify this. So this is going to be 1 over 1 minus p plus 1 over 1 minus p squared. I'll do this. Multiply the top and the bottom by the same thing, and then I'll add these two things together. Where's my A?
Second term should be P over 1 minus
P over 1 minus P. Second term. So this thing right here, let's just back up. I ended up -1. Make sure we can all do this. This part was right, but I forgot to multiply in that part. So I make mistakes, everybody makes mistakes. I can recognize it's gonna be the wrong answer. So that's an interesting skill. And so I always ask you to double check your answers. Does that look right? You know, is there something about it that looks wrong if you've given it a sanity check? I'll let you think about why that can't be the right answer. But this is 1 over 1 minus P squared. So basic college stuff, mess up on it all the time. Just be careful. There's our answer. What's this? P times 1 minus P over N. The variance of each xi is P times 1 minus P. Ask yourself if you can prove that. If you can't, go and do it. So basic stat 101 question, but figuring out the expectation of x is really easy, it's P. Figuring out the expectation of x squared is really easy. And so then you just have the expectation of x squared minus the expectation of x all squared. Do that, we'll come up with P times 1 minus P. What happens when I divide everything by n? The variances start shrinking by that rate. So stat 101. So let's write down what we've got. So this whole thing is normal P, 1 minus P, 1 over 1 minus P squared, squared again, and then times P, 1 minus P over N. And this is kind of distributive like that. And if I knew P, I could use that as an answer. But the whole point is we don't know P. If I did know P, I would have just told you what I thought P over 1 minus P was. It would just be a calculation for you. And so we can use this thing to estimate. This is what you'll be doing on your homework. You're going to pretend you don't know P. And what we'll use in practice to estimate GP, P over 1 minus P. Somebody tell me what we usually call this number that we're calculating? The odds. Why do people like thinking about odds instead of just P? I don't know, to tell you the truth. It's certainly a harder estimation problem. Having something in the denominator that wiggles around certainly perturbs this estimator more than just estimating P. So it's an interesting thing. I like people to talk about P because it's an easier estimation problem. We'll talk about that, and you'll notice it in your simulation study. Let me just allude to what can happen in a bootstrap. Imagine P was small. Well, let's say P was large. Both things will cause you problems. One of them you won't even be able to compute. Let's say P was really large, 0.99. So I'm going to ask you to do these simulations as functions of different P's and see how well it works. When P's in the middle, we usually do pretty good. But when it's pushed against the endpoints, we usually do much worse. And so boundaries do things to us and mess up all our asymptotics. But think about the bootstrap. If P were real large and let's say n was pretty small, n was 10, and P was 0.99, it wouldn't be all that surprising if you got a vector full of ones. And even if you got even just 1, 0, when you bootstrapped over that, every once in a while you just get a bootstrap replicate of a bunch of ones. And so when you go to compute this thing, you're toast. So, fail. So we're going to start to notice bootstrap can fail. Sometimes it works. And I want you to report that back and say when it fails, how often it fails, things like that. And then I'm going to want you to apply the delta method using this approximation. So the bootstrap will give you a distribution. And the delta method also provides you an insight about a distribution. However, I can't use this yet because I don't know P. It would certainly be cheating to use it. Again, if I knew P, I'd just use it. So anytime I ever ask you to estimate something, and if you tell me that you need to know the truth to estimate it, that's certainly decreased points. So in practice, what we use is we use this. Normal P hat, 1 minus P hat. 1 over 1 minus P hat squared, squared. P hat, 1 minus P hat. So say you're a frequentist, an asymptotic frequentist in this case, because I'm not exactly right. I'm making not quite right probability statements, but as n gets bigger, I do better. So I start to have correct frequency interpretations of things, or close to it. If I were to build confidence intervals out of this, my interpretation would be those confidence intervals would cover true P over 1 minus P, 95% if I ended up looking at 0.25 and 97.5 quantiles. So 1.96 deviations from this number. I would hope that those would cover 95% of the time. And if you call yourself a frequentist and you don't check, you're not a frequentist. So you've got to check. So how good is this to your 95% statement? I'm not going to ask you to check that explicitly, but I'm going to ask you to report things like means and variances. Okay. So this is how we use this tool. Chapter 10 does all this. So if you go to chapter 10, they'll compare the bootstrap and this to each other, and they call it the asymptotics chapter. So if you want to read that, that's cool. It's got a little bit of insight on this problem. It's got numbers for you computed in tables. But they do some of the math that we've been alluding to, and they also do simulation study in that chapter. We're never going to touch chapter 10 other than me just saying, this is in chapter 10. So we're going to get that stuff as we go. Okay, any questions about this before I switch gears? One more. One more example. This one's a little bit fun. So expectation of x bar, in this case, is equal to mu. So xi's are normally distributed, mean mu, variance sigma squared. I've stopped writing IID, but I mean it. I want you to estimate this thing. Apply the delta method. So, because we know properties of x bar. And so g prime mu equal to 2 mu. So the delta method. G mu hat x bar. When I estimate a parameter, we throw a hat on it to indicate it's not the actual true thing. It's what I think it is. So this is going to look normal with a couple parameters in here. And so what do I plug in right here? G mu. Which is just mu squared. No big deal. And what do we plug in here? 2 mu squared. That's my derivative times my variance. Of x bar. So what's the variance of x bar? Sigma squared over n. If I wanted to use the delta method, I would put hats on all of this, and I'd plug in x bar. And this thing right here, I'd estimate that as well. So I'd estimate everything if we're going to use this thing. The delta method might be okay, but it certainly depends on what mu is. So let me just point out, if mu were equal to 0, we just wrote this. G x bar is kind of like you don't check and you say you're a frequentist, I'm always going to say, well, they're just kind of telling you something. Might work out theoretically. And unless they check to say that it actually worked, I just replaced the word asymptotic frequency with kinda. This was via 0. So mu squared, plugging in mu is 0, that's a 0. And this thing is a 0 as well. So 0 squared, if you will, times sigma squared over n. This is all 0. So I just wrote down that it's a normal centered at 0 with variance 0. So I estimated it with a point. Now I could come back and say, well, math told me to do this. So that's why I do it. And I could try to defend this, but it's just silly. And so the problem is G prime was 0. So that's a huge problem. So what do you do in cases like this? Imagine you're in the 1960s. Do we know what the answer to this is? So x bar squared. How is this distributed? It's a chi-squared. Which chi-squared? What's that?
X squared n over n.
This one's going to be a 1 right here. We're taking something normal, but it's a scaled chi-squared. So sigma squared over n. You want to just think of it as a chi-squared that's multiplied by something because the variance is off. But that's what it is. So it's a scaled chi-squared. They're always positive. They should be. And this answer even says, doesn't say much. So this is a ridiculous approximation to that. The problem lies with G prime with 0. So 1960s, I'm sitting there, I need an answer for somebody, what do? Second order Taylor approximation. And now I have xn minus theta, or using the book's notation, yn minus theta squared in my second order term. When I go to analyze the distribution of that statistic minus the mean squared, it's no longer normally distributed under the assumptions. The assumptions were that thing was normally distributed, but now I'm squaring it. So squared normals are chi-squared. So the second order delta approximation entails a chi-squared distribution. Let me ask you this. So the first order delta approximation, delta method, gives you a limiting normal distribution. And the second order one gives you a chi-squared. But I have to use the second order one only when the first order one fails. Why not always jump to the second order Taylor method?
Save some time.
What's that?
Save some time.
Save some time, maybe. So that's not the answer though. I just want you to remember that our approximations, this was equal to G, wherever I want to center this thing, theta, plus G prime theta yn minus theta divided by 1 factorial plus G prime double prime theta, second derivative, divided by 2 factorial, which is just 2, yn plus theta squared. This thing is normally distributed. In the first one, we don't use this other part. If G prime is 0, this part is chi-squared distributed. If this isn't 0, right here, and I use both of them, I'm adding a chi-squared to a normal. And in 1960s, that wasn't useful. They've got their chi-squared tables, they've got their normal tables, but they don't have chi-squared plus normal. What's chi-squared plus a normal random variable? I have no idea. Never used it before. Quite cumbersome. Why would I ever do anything like that? So we don't even know what that distribution is. It doesn't have a nice form.
Is that y minus theta squared?
Yes. Absolutely. So that's why this is 0, we can jump to that term. But if that's not 0, it's rather inconvenient to put this in. You might think, go farther and farther down, but what's a normal cubed? I don't know. So what's a normal raised to the 7th power? I don't know. So this approximation technique is not very helpful because I need to start learning about all these distributions that I don't even know about. It would be easier to just address Elise's question, just transform the random variable if you're going to have so much difficulty with this. Okay. That's ultimately what a Bayesian will do, and I'll show you how to do that. We've got 8 minutes. Let me give you a brief introduction. Any questions? Last year when I did this, it was a week later. We're doing great this year. We're getting it. So if we need to slow down, you guys can let me know. Let's just talk about a little bit of history of Bayes, and soon I'm going to tell you about Monte Carlo. Okay, so these things are going to go hand in hand. I did a Google search on the term Bayes, and if you've seen this before, it's worth seeing. So, I did a Google search. This is real. I just did a query search, and I searched on words like Bayesian, Bayes, Bayesian. Google did the stemming for me, and they told me where the word coincided with dates on articles. So certainly nobody had uploaded a document onto the internet in 1760 and used the word Bayes, but it's being referenced historically with that date. So, and this is about as good as Google Trends and stuff like that will do for me. So I don't use this as a real analytical tool. I think it's heavily flawed. The way it baselines and normalizes stuff is really weird. And the way it rounds things next to edges is really weird. I did this search in 2007 when I first showed up here. And so certainly the term usage was not going down. It's certainly going up. And if we did this thing again, we'd see that it's climbing. So Google Trends does all kinds of weird rounding, normalization, density approximation stuff that I never understand anyway. Every time you employ it, it does it differently. So careful with that data. But it gives us an overview, just a quick overview of what's going on. So we can take this with a grain of salt. So Bayes is exploding. What happens here? Why this hook? Computers. MCMC, Markov Chain Monte Carlo, Metropolis Hastings, the most important algorithm of all time. So, not according to me. IEEE said. So how convenient. So if you're here for a couple review sessions, since this just came to my mind, Shane will be covering review tonight, because I have to go out to dinner tonight. And I will have an extra review session Friday after class. So Shane should be able to do this stuff, and then I'll include another review if you need it after Friday's class. So business as usual, nothing's changed.
Aren't the reviews normally Thursday?
That's what I always mean to say.
Okay.
So I say Wednesday because I've done it a lot on Wednesdays, but I always mean Thursday for this class. It never changes regardless of what I say. So I just can't help myself. Okay, computers, MCMC, Metropolis Hastings. We had a good conversation about that. Some of the history. What happened here? It's interesting. About the 20s. This is student tea. This is gossip. At Guinness. It's actually a Bayesian sometimes. They forgot to tell you. So he starts writing a whole bunch of stuff. What happened here?
Development of Bayes' theorem.
Yeah, Bayes' theorem. So, original paper stuff. So, all the originalities. Took a long time for people to really catch on and start using this. Stats wasn't quite a thing until about here. So, probability was certainly a thing, and a lot of people are just using probabilistic results to build games and win money. That's the origins. What's this? That's interesting. A ripple for a while. Sputtering?
Probably Fisher bashing games.
Maybe a little bit of that. Bashing himself. 1940s. World War II. So, Helen Ford, Bletchley Park, I.J. Good, who came here. So, they start doing a lot of Bayes to decrypt the Nazi code. We can talk more about that. It wasn't just Bayes that they used, but they obviously baselined things and things that they knew with built priors and used Bayesian procedures, understood shrinkage. They didn't always call it this, though. So Jack kind of came in and said, what we're doing over and over again is Bayes. Okay, just a little bit of history. Here's an evolution of Bayesian thought. So at the top of the tree, there's Laplace. He understands the implication of what Bayes knew. So I don't like to talk about something without talking about the other side. Never makes sense to me. I always have to compare. So I understand the context. If you're a good statistician, you understand that concept. It doesn't mean anything unless you compare. These are kind of the classicists, frequentists, those sort of guys. So we've got Pearson, Daddy, Baby, Egon, and Carl. We've got Fisher, we've got Nathan. Talk about those guys soon. So, mathematician, geneticist. So, doing biological studies. Biometrica is spelled with a K because of Carl. It's his journal. Biometrics is Fisher's journal. So, they're competitors. Here's the offspring. So, they got together, got into a war with him. Talk about that soon. These are some people over on the other side of the tree. Dave Finetti, Jeffries, Jack Good, named Bayes. So according to Steve Feinberg, his paper. Take my Bayes class, I'll ask you to read that and comment on it. So, but he came up with the term Bayesian. Didn't quite happen here, but he was here for the prominent part of his career. So Savage, Lindley, Good, we'll try to understand who they all are. Gelfand, anybody knows what he did? He did Gibbs sampling. So he makes the tool useful. Bayes. Berger, Adrian Smith come up with a lot of decision theory, particle filters, and MCMC, these guys together, all very cool. So MCMC is born, and that makes us useful. We don't have to argue on philosophical grounds, we can actually do the calculation. So next up I want to get into what Bayes' theorem says. I'll give you just a little bit more history, but then I'm going to show you in an example how we address this odds estimation question in the Bayesian. So we'll pick up there next time. That's it, you guys. Thanks.